Hello grade 10 students. Today we will be discussing the third lesson from your grade 10 science book, Structure of Matter. As you know, when we discuss the structure of matter, we will be mainly dealing with their chemical properties. So therefore, this is a chemistry based lesson. In order to start the lesson, you should first remember what matter is. If you look around you, in your environment, there are living beings and non-living things. And these non-living things can be divided into two types. One is matter, the other one is energy. To define matter, anything that has a mass and occupies space is called matter. Whereas anything that doesn't have a mass and that does not occupy space are known as energy. For matter, we can talk about any substance. Say a ball, a rock, water, air, all these come under matter. Whereas energy, heat energy, light energy, sound energy, likewise, you can go on giving examples for energy. And in this lesson, we will be mainly concentrating on matter. And that too, the chemical properties or basically the structure of matter. With that in mind, first we will look at the contents of this lesson. First, we will be discussing the planetary model of the atom. Since atoms are the basic units of matter, we will have to look at the structure and the model of atoms. Second, it will be the electronic configuration. As you already know, electrons are a type of subatomic particles and the arrangement of electrons is discussed under electronic configuration. Then we come to the modern periodic table. Since there are so many elements, there needs to be a classification which is given under modern periodic table. The next topic is isotopes. Isotopes are the different types of atoms present in an element. Thereafter, we'll be looking at the pattern seen in the periodic table. How the properties of elements change along the periodic table. Afterwards, we'll be looking at metals, nonmetals and metalloids. Those are the different types of elements present in nature. And finally, we will discuss how to write chemical formulas when atoms combine and form compound. Okay students, now we will start the lesson by discussing what matter is. So as you can see, the things in our environment can be classified into two main categories as matter and energy. Under this, we will be discussing matter. And matter can be classified based on its property in mainly two different ways. That is based on its physical property or according to the physical nature and according to the chemical composition. First, we will just look at one example as to how we will be classifying matter based on physical nature. When we say physical nature, if you take an object, say a box, you can touch it and feel it. It will be hard or it can be brittle, it can be very strong and it can exist in different states. Three different states of matter: the solid, liquid and gas. For example, if we consider the compound water, that is H2O, it can exist in all three states of matter. If we look at the states, if it is in the solid form, we call it the ice. And in the liquid form, it is water. And in the vapor form, we call it the water vapor or steam. So that is based on physical state of matter. We will not be going into detail regarding the classification based on physical state, but we will concentrate on classification based on chemical nature of matter. So under this grouping, there are two main types. One is the pure substances, the other one is the mixtures. When we say pure substances, any substance that has a definite composition and is made up of only one type of substance is known as a pure substance. All the elements and different types of compounds in their pure form come under this group. Therefore, we divide it into two, the elements and compounds. So when we talk about elements, they are the pure substances which have definite properties and they cannot be divided into smaller independent components with definite properties by physical or chemical methods. That is, if we take iron as an example, you have a piece of iron rod. By applying a physical change or a chemical change, you can't convert it into a different substance that has specific properties. If you divide it, it's still going to be iron. Then it's known as an element. But when these elements combine in a fixed ratio, they form compounds. Compounds also have definite properties and they also cannot be broken down into individual components by physical methods. So, the elements form the compounds and elements have specific properties. When they combine chemically, the compounds have different properties. For example, if we look at all the elements, we have iron, oxygen, copper and nitrogen. Those are a few examples. Out of these, if we take oxygen combining with hydrogen, we get water. The properties of water are different from hydrogen and oxygen. Similarly, carbon dioxide. Carbon has certain properties, oxygen has certain properties, and carbon dioxide has properties of its own. So, all these, the elements and compounds, are pure substances with definite characteristics or properties. Then what happens is they combine more than one pure substances, two or more pure substances combine together and form mixtures. For example, if you have salt, a compound, water, another compound, they mix together and form a mixture. Oxygen is an element, water is a compound. When oxygen dissolves in water, we have mixtures. And these mixtures can again be divided into two types based on how their composition is distributed throughout the mixture. So we have homogeneous mixtures. Homo means same. If the composition of a mixture is uniform throughout its bulk, then it is known as a homogeneous mixture. For example, we take salt, the first example, salt solution. The salt exists as crystals and water is a clear liquid. You mix them together, you get the salt solution. Once it's mixed completely, you cannot differentiate salt from water. And throughout the solution, if it is salt, of course, we don't drink a lot, but let's say we have sugar solution or a fruit juice, lime juice. If we take the first sip, there is a certain taste. And we drink the juice and we take the last sip, still the taste is the same. So that means the composition of the lime juice had been uniform throughout the mixture. So therefore, it is an example for homogeneous mixture. Similarly, sugar solution is a homogeneous mixture. On the other hand, we have heterogeneous mixtures. Hetero means different. So as the name implies, you can understand the composition is not uniform throughout the solution. One example is lime water. Here the lime means calcium carbonate or calcium hydroxide, what you get from the limestone. When you dissolve this white color substance in water, a certain amount of it dissolves, but if you stand it for some time, if you just keep it on the table for some time, you can see the white color substance depositing towards the bottom of the solution. So the bottom part will be more whitish or milky in color, and the middle part will be lighter in color, and towards the surface, the solution will be more clear, like water. That means the composition is not uniform throughout the solution. So therefore, it is a heterogeneous mixture. Another example is rice and sand. Say by mistake, there is a little bit of sand mixed with rice. So it's a common mixture, but you can identify the rice grains from the sand particles in the mixture. At the same time, at one part of the mixture, there can be more rice, less sand, and at another part of the mixture, there will be more sand and less rice. So therefore, the composition of this mixture is not uniform throughout the mixture. Therefore, it's a heterogeneous mixture. So I hope students, you all have a very good understanding about the different types of matter according to their chemical composition. But all these substances have one common property. They are all made up of the same building unit. That is the smallest unit that makes up matter. It is what is called as atoms. So now we will look at what atoms are and their structure. Atoms, as I said, are the building units of matter. And these atoms can chemically combine and they have specific properties. So to know about atoms, we should first know what atoms are made up of. They are made up of subatomic particles. And there are three types of subatomic particles. When we discuss about subatomic particles, you should know their name, the symbol, the charge, and the mass of subatomic particles. The first particle or one of the subatomic particles is protons. And the symbol given is simple P. It has to be all simple letters. And the charge of proton is positive. Protons are positively charged subatomic particles. Then we have the second type, neutrons. As the name implies, this does not have charge, neutral subatomic particles. neutrons are given the symbol simple N, and this has no charge or zero charge. You can even take the charge as 0 or say no charge. And the third type is electrons. We use simple E, and this has negative charge. So the three subatomic particles combine in different ways and in different numbers to make up different types of atoms. But the common feature is that there are equal number of protons and electrons. So because the protons are equal to electrons in number, the number of positive charges are equal to negative charges. Therefore, atoms are electrically neutral. Therefore, you have to remember atoms are electrically neutral. Now we will see how these subatomic particles are arranged in an atom. So to know that, we discuss model of an atom. Now scientists got the knowledge about atoms and subatomic particles throughout the years, and they wanted to explain how these atoms get their special definite properties. So in order to do that, there were different scientists who proposed different structures or models for atom. But only a few of those structures were accepted models. The first accepted model of atoms is the nuclear model. And this model was put forward by a scientist called Ernest Rutherford. Students, you have to remember the name of the model and the name of the scientist who proposed the model. Now we will see why the name nuclear model came into place. If you take the atom, if you imagine the size of the atom as a huge football ground. Now this space is a huge football ground. And in the middle of that ground, there is a teeny tiny space, a very small space, the size of a chickpea. That is called the nucleus. If you look at this diagram, you can see this tiny part is the nucleus of the atom. It is called the nucleus. And inside the nucleus, there are two subatomic particles, the protons and the neutrons. So because Ernest Rutherford proposed the concept or put forward the concept of nucleus first, we give the name nuclear model. And around this nucleus, all the electrons, that's the third type of subatomic particle, go around in a circular motion or a certain path. Here you can see in this diagram, these are electrons which are moving around the nucleus. Now this model was compared with the solar system where the sun is similar to the nucleus and the electrons that revolve around the nucleus are similar to the planets. Therefore, the same model was given the name the planetary model of atoms. So it's basically the same model. Because of the introduction of nucleus, we call it the nuclear model, and because it resembles the solar system or the planets, we call it the planetary model. Okay. Now in this, the positively charged protons are in the center. Positive charges are in the center. And the negatively charged electrons are moving around this nucleus. Normally, the positive and negative charges attract each other. In that case, these electrons should get attracted to the nucleus and come and fall on it. But that does not happen. Does not fall on the nucleus. The reason is electrons revolve very fast around the nucleus. So, because electrons are revolving very fast, the position of the nucleus and the electron are maintained. They do not collide with each other. So, this is the basic model that was accepted by the scientists. Further, the same model was illustrated and more information was provided by another scientist called Niels Bohr. Now, we will look at the structure proposed by Niels Bohr. So, Niels Bohr is another scientist who proposed the structure for atom. It's based on the structure proposed by Ernest Rutherford. So, here also we have the positively charged protons and the neutral neutrons inside the nucleus. And around that, Niels Bohr said electrons revolve in definite paths. And these paths were circular in shape. Like this, there are definite paths, and the electrons are contained in this path and they move around in circles. And these paths are called shells. We have special names. They are known as shells or energy levels. Now, there can be different number of electrons in different shells. Shells because they are around the nucleus and since it is a definite path. And we call them energy levels because each of these shells have specific energy. They have specific energy, and usually the energy increases when you go from the nucleus towards the outside of the atom, towards the periphery of the atom. And these shells are given different names or numbers. We number them starting from the shell closest to the nucleus. So, the first one closest to the nucleus is 1, 2, 3, and if there is another shell, 4, 5 and so on. Similarly, we can use English alphabets to name these shells. And it starts with K. Capital K is the first shell and capital L is the second shell. M is the third one, and if we had a fourth shell, it would be N. And starting from 1 to 4, 5, 6 and also KLMN, the energy increases. But the energy difference between two shells decreases. Energy increases, energy difference decreases. That is the reason why there is more space between the nucleus and the first shell, but as you go away from the nucleus, the space between the shells decreases, because it shows us the relationship between the energy of shells or energy levels. So students, now you would have got a good understanding about the most accepted and modern model of atom, the Niels Bohr model, which was mostly elaborated based on Rutherford's model, and the structure of the nucleus with protons and neutrons, and the energy levels containing electrons. Now we will look at some 3D animation models of how an atom is and how the subatomic particles are present in an atom. Okay, now here students, you all can see the model of a hydrogen atom. And in this model, you can see the nucleus in the center, in which the proton, there is only one proton in the hydrogen atom. So you can see one proton there, and there is only one shell. And in that one shell, there is one electron that is revolving around the nucleus. So this is the basic Niels Bohr model of an atom. Now we will look at another more complex atom that has more number of electrons and protons. So we will look at a carbon atom. Now you can see students, the carbon atom has both types of particles in the nucleus, the protons and the neutrons, and you can see there are more than one shells. There are two shells or energy levels around the atom, and you can see in one energy level the electrons are going around in the anti-clockwise direction, and in the second energy level the electrons are revolving in the clockwise direction, and they don't move from their energy levels. They are confined to the energy levels, and they revolve around the nucleus only in that definite shell. That is very visible to you from this animation. Now we will look at a little bit more complex model of an atom, that is the atom of a potassium element. This has 19 electrons, protons and 20 neutrons. So there are 4 energy levels. And you all can nicely observe that the protons and neutrons are confined to the nucleus, and also the electrons moving around without colliding with each other and without jumping from one energy level to the other. They are moving around in their fixed definite path. That is the shell or the energy level. With this, you would have got a very good understanding about the model of an atom. Next, we will see how electrons are arranged in these different energy levels. As you can see, Niels Bohr, who further elaborated the Rutherford's model, stated that the electrons move in definite paths called the shells around the positively charged nucleus. So, nucleus is positively charged, electrons are negatively charged. There is an attraction between the two, but they don't collide with each other because of the fast revolving of electrons in their definite path called the shells. Another name for shells is energy levels. And as we discussed before, the energy levels are assigned numbers 1, 2, 3, 4, starting from the one closest to the nucleus and going outwards, or else we give the letters Kl, Mn, again starting from the closest to the nucleus. And all these energy levels can contain only a fixed number of electrons in them. So now we will see the maximum number of electrons that can be present in each energy level. You will see that when you start from the energy level closest to the nucleus, as you go out, the number of maximum electrons will increase. So, in the first level, that is the K shell, there can be only 2 electrons maximum. There can be 1 or 2 electrons. But in the second shell, that is the L shell, there can be a maximum of 8 electrons. That is the maximum value. So, there can be an atom that has 1 electron in the second shell, 2, 3, 4, up to 8. So, there are 8 different atoms possible because there can be 8 electrons in the second shell. If we look at the third shell, the M shell, there can be a maximum of 18 electrons. And in the fourth shell, that is the N shell, there are 32 electrons possible. So, as you can see, 2, 8, 18 and 32. And remember students, when electrons get added to these energy levels, first they fill up the first shell, 1 and 2, then another 8 go to the second shell, only one that is completely filled, they will go to the next shell. Now we will again look at a summary of the model of an atom with the nature of the energy levels. As you can see here, the nucleus of the Niels Bohr model is shown in the center and all the energy levels are shown around it. If you look at these energy levels carefully, as we discussed before, you can see the distance between energy levels K and L is more than the distance between the L and M shell, and the M and N shell has a very small distance between it. The reason you already know. What is it, students? Yes, because the energy of shells increase from K to N shells of coming out of the nucleus. But the energy difference decreases. At the same time, there are a maximum number of electrons possible in each of the energy levels. If I denote that, you will be able to see that the first shell can have 2 electrons, the second shell can have 8 electrons, third one can have 18, and the last one can have 32 electrons. So, as you start from the innermost shell, 2, 8, 18 and 32 electrons are possible. As you know, students, atoms are made up of subatomic particles, and this is the model of atoms. And all these atoms are the basic units of all matter. But as you know, matter, different substances, different elements have different properties. Carbon is different from iron, iron is different from oxygen. So that means the atoms that make up these elements have to be different from each other. That is possible because of the different number of subatomic particles present in each atom. Based on that, atoms have unique properties called the atomic number and mass number. And out of these two, atomic number is very specific to each type of atom. Now we will see what atomic number is. Atomic number. The atomic number is the number of protons in an atom of the element. You already know that there are equal number of protons and electrons. But out of these two, the protons are contained within the nucleus. So they cannot go out of the atom, or additional protons cannot be put into the atom. So each atom of an element has a fixed value of protons, and this number of protons is defined as the atomic number. So the atomic number of the element is equal to the number of protons in an atom of the element. If we look at some examples, first we will see sodium. Now sodium element has 11 protons, 11 electrons and 12 neutrons. Out of this, the number of protons is taken as the atomic number. So for sodium, the atomic number of sodium is 11. And for atomic number, we give the symbol Z. So we can write capital Z is the symbol for atomic number. Z of sodium is equal to 11. At the same time, the number of protons are equal to number of electrons. So in other words, we can say the number of protons equals the atomic number. Therefore, the atomic number equals the number of electrons. But we don't consider electrons for atomic number. I will explain that after this. The number of electrons can change in an atom when atoms involve in chemical reactions. We will look at another example. We will take the chlorine element. Let's say chlorine atom. Now the chlorine atom has 17 protons, 17 electrons and 18 neutrons. So what will be the atomic number of chlorine? Yes, it is going to be the value 17. So atomic number of chlorine is equal to 17. Like this, if you look at all the elements, atoms belonging to the same element have the same number of protons and electrons, and they have the fixed atomic number. Therefore, the atomic number of elements is a unique characteristic of that element. That is like the identification of an element. If we say 17 atomic number, it has to be chlorine. Similarly, if we say atomic number 6, then you should know that it is carbon. When you learn about all the different elements which is there in your syllabus, you will have to remember the atomic numbers of the first 20 elements. Now, we will discuss why we don't define atomic number based on the number of electrons. Although the number of electrons are equal to the number of protons in a neutral atom. So, for this, we look at what ions are. Ions are the atoms of an element with a charge. This happens when elements involve in chemical reactions and the atoms form bonds, forming compounds. So, we'll take an example, sodium. The sodium atom has 11 protons, 11 electrons and 12 neutrons. If I put this into the atomic structure, this is the nucleus which has the protons and the neutrons. Around the nucleus, all these electrons are going to be arranged. There are 2 electrons here. Then we have 8 electrons in the shell. And outermost one will have only 1 electron. So what can happen is you can remove this electron from the outermost shell. So then what will happen? You will have a sodium where you have the same number of protons and neutrons, but there will be less number of electrons. There are 11 electrons in a neutral atom. We remove 1 electron and then the atom has only 10 electrons. But there are 11 protons. So that means 11 positive charges but only 10 negative charge. Therefore, there is an additional positive charge there. We can represent this in this manner. The sodium atom losing an electron. Normally, losing an electron we don't write as minus. Instead, we write as plus electron on the right hand side of the equation. And we put a positive charge for the sodium symbol. That means this is an atom and this is a positive ion. Similarly, we can add an electron to an atom. For example, if we take a chlorine atom and we add 1 electron to the chlorine atom, we will get chlorine minus. That is a negative ion. In this negative ion, you can see chlorine, the atomic number is 17. We discussed that before. So, there are 17 protons and 17 electrons here. But when the negative atom forms, there are 17 protons. The atomic number is the same, but there are 18 electrons. So, as you can see, when sodium and chlorine involve in chemical reactions, the number of electrons are changing. Sodium is losing electrons and chlorine is gaining electrons. Therefore, the number of electrons in a particular element is only fixed when it is a neutral atom. But it can vary when there is chemical reaction taking place. That is the reason we consider only the number of protons for the atomic number. For atomic number. And this is a unique property of atoms. I hope you all understood this very clearly. Now we will look at the second property of atoms, that is the mass number. Mass number. Now we discussed there are three types of subatomic particles, and out of those three particles, the protons and the neutrons have a relatively high mass. So here you can see the mass of protons and neutrons is high and also is equal. But if we look at the electrons, they are 1 over 1840 times lighter than protons and neutrons. So comparatively, the mass of electrons are negligible. Therefore, the mass of an atom is obtained from the mass of protons and neutrons. So mass of atoms come from mass of protons and neutrons. And these two are situated in the nucleus of an atom. The sum of the number of protons and neutrons in the nucleus of an atom is called the mass number. So as you can see, mass is obtained only from protons and neutrons, and they are contained within the nucleus. Therefore, the mass number of atom is defined as the sum of protons and neutrons in the nucleus of an atom. So you can see mass number is equal to number of protons and number of neutrons. The symbol for mass number is capital A. So A of an atom, that is the mass number of atom, is equal to number of protons plus number of neutrons, which have the mass. So for example, if we take again the sodium atom, you will remember by now, sodium has 11 protons, 11 electrons and 12 neutrons. Out of these, we need to take the number of protons and the number of neutrons. So the mass number of sodium, A, will be equal to 11 plus 12, that is 23. So students, you have to remember how you should calculate the atomic number and the mass number for an element or an atom of an element. Atomic number is equal to the number of protons, mass number is equal to the sum of number of protons plus neutrons. And the atomic number is a unique property. We will see the mass number can vary. When we have these two properties, we give a standard symbol for the atom and we write a standard representation of the atom. Now we will see how we can write that. So there is a standard way of writing the atomic number and the mass number of an element. You have already learnt in grade 9 that we give different symbols for atoms of elements, and it is a capital letter of the name of the element either in English or in Latin. So here also we use that particular symbol. For example, sodium, the Latin name is natrium, and the two letters N in capital and A simple. We write that, and then on the left hand side of the symbol, we have to write the atomic number and the mass number. I will show you all how. So in sodium, we have 11 protons and 12 neutrons. If I calculate the atomic number Z, that is equal to the number of protons, so that is equal to 11. Whereas the number of neutrons is 12. So the mass number A will be equal to sum of protons plus neutrons, that is 11 plus 12, we have 23. Atomic number of sodium is 11, mass number of sodium is 23. Then we write the standard symbol of sodium, Na, and we have to write these two values on the left hand side. So left hand side, we write the mass number on top and the atomic number at the bottom. 11 is the atomic number, 23 is the mass number. So if I show you all or write the common standard symbol for the atom of an element, I'll take the atom of the element as X, and on top we have A mass number and Z atomic number. Atomic number, and on top we have mass number, and this is the standard representation of an atom of an element. We will look at another example, the chlorine atom. First, y'all think how you're supposed to write the standard symbol for a chlorine atom. Then you can check with this. Yes. First, you have to calculate the atomic number and the mass number. Atomic number is direct. Z is equal to number of protons, so 17, and number of neutrons are 18, so the mass number A is 17 plus 18, that's equal to 35. Then what do? We write the symbol Cl, capital C, simple L, and mass number on top 35, and atomic number at the bottom 17. So when we read out the element, we say 35, 17 chlorine. We will look at one more example. We will take carbon, the element carbon, a carbon atom. Students, once we finish this lesson, you will see that you have to remember the first 20 elements, atomic numbers from 1 to 20. Then you will remember all these values easily. So for now, for carbon atom, there are 6 protons, 6 neutrons and 6 electrons. All are equal. So if we are to write the standard symbol, we have to find the atomic number Z equals to number of protons, that is 6, and the mass number, number of protons plus neutrons, 6 plus 6, 12. And the standard symbol will be 12, 6 carbon. And remember students, in case they do not give you the number of protons, instead they give you only the number of electrons and neutrons. Then you can remember that the number of electrons are equal to number of protons in a neutral atom. So therefore, we take the same number of electrons for the Z. Although the definition says number of protons is the atomic number, when you are given number of electrons, you can use that value only. So with these examples, you would have a very good understanding about the atomic number and mass numbers of different atoms of different elements. Now, we will use a simulator to see the different properties of atoms of elements, how the subatomic particles combine, and how neutral atoms and charged ions are present in nature. Now we will see how we can build up different atoms of different elements. We'll take the most simplest element, hydrogen. Hydrogen has only one proton. You can see the name comes. Now it has a positive charge because there's only a positively charged proton. To this, when we add an electron, the positive and negative charges cancels off and you can see it's a neutral atom. Also, you can note the mass number there. Although there are two subatomic particles, there's only one mass number because it's only the proton that gives the mass number. Now we look at the helium element. This has two protons and two electrons. Two protons, two electrons, but still it is unstable because I have to include the neutrons. So in a helium atom, there are two protons, two neutrons. So therefore, the mass is 4. And there are two negatively charged electrons. Therefore, the atom is neutral. So likewise, we can keep on adding neutrons, protons and electrons. We will look at another example, carbon. Carbon has 6 protons and 6 neutrons. You can see the mass number changing. And finally, when we add 6 protons and 6 neutrons, the mass number becomes 12. But the charge is there. We don't have enough electrons. I'll have to add electrons. As I said, there can only be 2 electrons in the first energy level. Therefore, the third electron goes to the second energy level. So, I will add 4 more electrons. So, now you can see the atom is neutral. There are 1, 2, 3, 4, 5, 6 electrons, 6 protons. So, that means the atomic number is 6 and 12 protons and neutrons together. So, the mass number is 12. Likewise, when the number of subatomic particles get added up, there are different types of atoms formed. As you can see, we will be discussing the periodic table later. There are so many different types of atoms. All this is possible because of the various combinations of subatomic particles. Now, we already discussed that there can be a maximum number of electrons present in each energy level. Now, we will look at another element, fluorine. Fluorine has 9 protons and 9 electrons and 10 neutrons. So, can you all guess the atomic number and the mass number of fluorine? Yes, fluorine has atomic number 9 and mass number 19. So, I will have to add another 3 protons and 4 neutrons, and in addition to that we need to put in electrons, 3 more electrons. So here you can see there are 9 protons, 9 electrons, 2, 3, 4, 5, 6, 7, 8, 9 electrons. So therefore the atom is neutral and the mass number is 19. But as you know, to an atom we can add electrons and remove electrons. When we add an electron, the atom gets a negative charge, therefore we call it a negative ion. So for fluorine, if we add another electron here, you can see it has a negative charge and it becomes a negative ion. And if you look at the top here, there are 9 protons, 10 neutrons. That value has not changed, but the number of electrons now has become 10. Therefore, it is a negatively charged ion. If it had been the atom like before, here you can see the number of electron is back to normal, the neutral atom. Similarly, you can look at the charges here. The positive charges and the negative charges are equal. So, it is a neutral atom. But once we put in another electron, there is an additional negative charge. So, the atom becomes an ion, a negative ion. Similarly, there are elements that can lose electrons and become positively charged ions, which are known as positive ions. For that, we can take the example, the most simplest atom, what we saw before, is hydrogen. In a hydrogen, there were only 1 proton, 1 electron and 1 neutron. I'll go back to the same atom. Here you can see when we keep on removing the subatomic particles, the elements changes that you can observe there. So, different elements with different combinations of subatomic particles. Now, we have come back to the simplest basic element, hydrogen. It has 1 positively charged proton, 1 negatively charged electron, and it is a neutral atom. The charges are equal. From this, I can take out an electron. Then you can see it becomes positively charged. So, look at the number of subatomic particles. Now, there is only 1 proton. No neutrons, no electrons in the ion state. So, that is why, students, we take the number of protons as the atomic number and not the number of electrons. But whether the atom of an element is in the neutral atomic state or an ionized state, the atomic number and the mass number do not change. It is the same. Only the number of electrons changes. And also, atomic number is a unique property of atoms. which will never change. That is the identity of an atom. But the electrons, the number can change. Now we will see how we can arrange these electrons into different energy levels. So the arrangement of electrons into energy levels of an atom is known as the electronic configuration, representing how electrons are filled in the respective energy levels from the one nearest to the nucleus of an atom outwards is called electronic configuration. You can remember the energy level, that is the first shell or the K shell, has the lowest energy. And when we move outwards from the nucleus, the energy of the shells increases. So when we arrange electrons into atoms, they fill up the shells with less energy first and then they go into the higher energy shells. That is where we have the electronic configuration and the arrangement of electrons. We will do an example, sodium. The sodium, by now you all know, has atomic number 11 and mass number 23. So that means there are 11 protons, that is equal to the number of electrons. So therefore there are 11 electrons. If I represent this in the model of an atom, the protons and the neutrons will be within the nucleus. Then we have the different energy levels, the first shell, second shell and the third shell for now. In this, the first shell or the K shell can only have a maximum of 2 electrons. So we add 2 electrons here, 1 and 2. So I have added 2 electrons to the K shell. 2 gone from 11, we have another 9 electrons. And the second shell can have a maximum of 8 electrons. So then I can fill up 8 electrons here. 1, 2, 3, 4, 5, 6, 7, 8. So I have added 8 electrons to the second energy level. 2 plus 8, we have already allocated 10 electrons to 2 energy levels and they are filled with the maximum number of electrons. So the last electron, the 11th electron, will go into the third energy level. So I have put the last electron to the third energy level. So here this shows that there are 2 electrons in the first shell, 8 in the second and only 1 in the third shell. That is how the electrons are arranged in the sodium atom. And when we write this arrangement in an order, we call it the electronic configuration. So the electronic configuration of sodium is 281. We will do another example, calcium. I will draw the atom of the calcium here. Before that, we will need to know the atomic number of calcium so that we can get the number of electrons. Calcium is 40-20 calcium. So that means there are 20 electrons in calcium. For this, if I draw the structure here, the nucleus containing proton and neutron, the first shell, second shell, third shell, and the fourth shell. So out of these 20, first shell can have 2. The second shell can have 4 plus 4, 8. So 2 plus 8, already 10 electrons have been assigned. Another 10 more electrons. In the third shell, there are a maximum possible number of 18 electrons. But here we can only allocate 8 electrons into the third shell. The reason is, in an atom, there can't be more than 8 electrons in the last shell that contains electrons. I will explain that. There are 10. We put another 3, 4, 5, 6, 7, 8. So we have assigned 18 electrons. But in the outermost shell that has electrons, there can't be more than 8 electrons. So if I assign the last 2 electrons to the third shell itself, there will be 10 electrons. That's not possible. So we have to allocate or arrange the last 2 electrons into the last energy level, that is the 4th energy level. I will arrange and write the electronic configuration for calcium. The first shell has 2 electrons. The second shell, you can see, has 8 electrons. The third shell again has 8 electrons. And the last shell, that is the fourth shell, has the last 2 electrons. So the electronic configuration of calcium is 2882. So remember students, although there are 18 electrons possible in the third shell, if that becomes the outermost shell that has electrons, it can't be more than 8 electrons. So I will write that as a note. Outermost shell with electrons cannot have more than 8 electrons. This is something that you all have to remember. But if it is a shell inside, not the outermost shell having electrons, it can be more than 8 and it can go up to a maximum of 18 electrons. I hope you all understood how we can allocate electrons to different energy levels. Now we will look at the different elements and how electrons are arranged into energy levels. So here the elements are given in order. It starts from hydrogen, the symbol is given, and you can see the atomic number starts from 1 and it goes up to 20. Students, you will have to memorize the order of these first 20 elements. The elements in order so that you know their atomic numbers as well. We have the first element, hydrogen. It has only 1 electron because the atomic number is 1. So when we write the electronic configuration, the electron goes into the K shell. Only one electron. Then it is helium. It has 2 electrons. So the 2 electrons can go into the first energy level. So here we write it as 2. We do not need to write zeros or any other values for the other shells. If you just write one value, it is understood that there is only one energy level. The third element is lithium, Li, and the atomic number 3. Therefore, the number of electrons are 3. The first shell will have only 2 electrons. Then the next electron will have to go into the second shell. Electronic configuration is 2, 1. Beryllium, Be, atomic number 4. So the first shell will have 2 electrons. The second shell will have 2 electrons. Then we have boron, atomic number 5. First shell again 2 electrons and the second shell has 3 electrons. Now you can see when the atomic number increases, the number of electrons in the second shell is increasing one by one. Then to carbon, 2 and 4 because the atomic number is 6. 2 plus 4, 6. So you should know to go from the atomic number to the electronic configuration, and in case they give you the electronic configuration, you should know to get the number of electrons, then the atomic number and the number of protons, which are all equal. Nitrogen, atomic number 7. So 7 electrons, 2 and 5. Then the next element is oxygen, atomic number 8. So 2 electrons in the first shell, 6 electrons in the second shell. Fluorine, atomic number 9. 2 electrons in the first shell and 7 electrons in the second shell. And neon, here you can see atomic number 10, 2 electrons in the first shell and 8 electrons in the second shell. Out of these elements, students, you all can notice that in these 2 elements, helium has only 2 electrons in the first shell. The maximum number of electrons possible in the first shell. And neon here, it has 2 and 8. That again, the maximum possible number of electrons that can be present in the first and second shells. So here, these 2 elements have complete shells. So here we can say they have complete shells. So there are certain elements which have electrons filled in all the energy levels. So we call them as atoms having complete shells. We will go back to the table. Here the next element is sodium. Sodium has 11 electrons. So 2 in the first shell, only 8 in the second shell. You can remember we can't write 9 there because the energy level, outermost energy level that has electrons can't have more than 8. And also the second energy level can only have a maximum of 8 electrons. So therefore, the next 1 electron goes into the third shell. So here you can see 1, 2, then from 2 the second energy level fills up, and then when we come to sodium, the third energy level starts filling up with electrons. We'll go to the next set of elements. The next one is magnesium, atomic number 12, so 12 electrons Now you know to write the configuration 282. That's correct. Then aluminium 13283. Silicon 14284. Then phosphorus 15285. Sulfur 16286. Chlorine 17287. Again we come to argon. Now 2, 8 and 8 electrons. This is also a stable configuration. And here also we consider argon as having a complete shells. Then we come to potassium. We have already seen the electronic configuration for calcium. Similarly, potassium also has 19 electrons. So we have 2 here, 8 here. We can't write 9 there because this is the outermost shell having electrons and that cannot be more than 8. So we have to write 8 here and the last electron goes to the 4th energy level. So the electronic configuration of potassium is 2881. Then we look at calcium. 20 atomic number. So 20 protons and electrons. Again we will have 2, 8, can't write 10 there. We have to write this as 8 and 2. So these are 2 elements where you have to remember although 18 electrons are possible in the third shell, it will become the outermost shell having electrons and that cannot be more than 8. So therefore, the 1 electron in potassium and the last 2 electrons in calcium go to the 4th energy level. So students, after writing the electronic configurations of all these elements, now you will be very familiar with electronic configurations and writing electronic configuration. At the same time, if they give you the electronic configuration of an element, let's say we'll take this 2, 8, 16. You should know to identify its number of protons, electrons and therefore the atomic number. What do? We just add them together. 2 plus 8, 10 and 16. So the number of protons and electrons are 16 and the atomic number is 16. You have to remember it is element sulfur. Or else after remembering all the first 20 elements, if they just give you the atomic number, you should know what element that is and also you should be able to write the electronic configuration. So now that you have a very good understanding about writing electronic configurations, we will look at some examples. So before going into examples, I told you all you have to memorize the order of the first 20 elements. I hope you have already done that. So with me, you all can also write down all the first 20 elements in order. It's going to be hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon. I will write the rest of the elements on this side. After silicon, it's going to be phosphorus, sulfur, chlorine, argon, potassium, and calcium. So you can see hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium and calcium. You have to know the order, you should know the standard symbol, and if you know the order, you can identify the atomic number as well, or you can remember the atomic number also. We will do a few examples. Let's say we will take boron. Boron has atomic number 5. Or else you can just count 1, 2, 3, 4, 5. Boron is the 5th element, so therefore the atomic number is 5. If it is 5, boron will have 5 electrons. And to write the electronic configuration, it is going to be 2 in the first shell and 3 in the second shell. We'll do another example. Let's say we'll take neon. Neon, the atomic number is 10. You can count and see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if neon has atomic number 10, then it will have 2 and 8. That's the electronic configuration. Then we will take another example. Let's say phosphorus. Phosphorus has atomic number 15. So the first shell would have 2, then 8, that is 10, and the last energy level will have 5 electrons. We go down the order, we come to argon. Argon has atomic number 18. So then it will have 2, 8, 8. 2 plus 8, 10, and 10 plus 8, 18. Then we have potassium. Again, to remind you all, the atomic number is 19. We will have 2, 8. We can't write 9. We have to write it as 8 and 1. And calcium, the last element, which has atomic number 20, 2, 8. We can't write 10. It has to be 8 and 2. So these are some examples of electronic configurations. To complete the symbol, I will write the mass numbers as well, but you don't need to memorize mass numbers. You should know to do the calculation, but you don't have to memorize them. You have to remember the atomic numbers and the order. Okay, students. So with this, now you will have a very good understanding about writing electronic configurations. So far we have discussed the structure of atoms, about subatomic particles, then the properties, atomic number and mass number, and now writing electronic configuration. So now you have a good idea that different elements are made up of different atoms because they have different number of subatomic particles. But there are a lot of elements in nature. We need to have a way of classifying them. Therefore, we will be looking at the classification of elements, that is the modern periodic table. So, modern periodic table. Now, you know, students, there are lot of elements in nature. So far, they have identified about 115 elements. It's really impossible to know all the elements, the symbols, and their characteristics. Even for scientists, although they deal with elements, especially chemists, in their day-to-day activities, they'll be using so many different elements. They do know the properties, but still they can't remember all the properties of all the elements. That's impossible for any person. So therefore, to identify and understand about different elements, and for our purpose to study about different elements, there should be a way of classifying these elements. The classification of elements is known as the periodic table. And over the years, again, scientists have attempted to classify elements in different ways, but none of those were very successful. The modern periodic table is the most successful and accepted method of classifying elements. And this was done by a Russian scientist called Dmitry Mendeleev. A periodic table for classifying elements was first introduced by Dmitry Mendeleev. We say first because this is the most accepted model. And in this periodic table, he arranged the atoms in ascending order of atomic number. So he uses atomic number for his classification and arranges the elements in ascending order of atomic number, and also he considers the electronic configuration. We have discussed these two by now. You all know very well how to write electronic configuration for elements. And when this is used and the elements are arranged into a periodic table, you will see the shape of a periodic table. We will discuss it in detail, but for now, I will just show you all a basic structure of a periodic table. This is how the very simple form of periodic table that you will be using for your level is shown here. And these are the places where we will be arranging the elements. And in this periodic table, you will notice that there are certain patterns and similarities. If you look at elements, when you arrange it in ascending order of atomic number, some elements will fall into a certain group, as we call it. We will look at that now. These elements will have similar properties. We can say similarities. And also you will see there will be a certain trend or a pattern in this periodic table. So, one purpose is to classify elements, arrange them in order, so you can compare the properties and identify elements very easily. And also, it is easy to study about elements, as well as if you find a new element, it will be easy to place that element in a certain position. Now, we will look at the periodic table in detail. Here you can see the modern periodic table is based on atomic number and electronic configuration. That I explained. Then I told you all that there will be a pattern as well as elements which belong to one particular area show similar properties. That is what is given by the periodic law. The periodic law states that the properties of elements are periodic functions of their atomic number. That is, when we arrange them like this. If you look at this side, 3, 11, 19, you can see there is an increase of 8. 3 to 11 and 11 to 19. So, similar elements, they are recurring with an interval of 8. And these 3 elements, lithium, sodium and potassium, show similar properties. That is what we mean by this periodic law. Not only this, if you look at elements like beryllium, magnesium, calcium, they show similar properties. On this side, you can look at elements like helium, neon, argon. They also show similar properties. So, the periodic table is based on atomic number and electronic configuration, and it shows or obeys the periodic law. Now, we will look at the proper arrangement of a periodic table. In this, you can see there are different colors given for different elements. And if we start from the first element, that is the most simplest one, hydrogen, with atomic number 1, it goes there. Then we have atomic number 2, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, atomic number 10, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium and calcium. Those are the first 20 elements, atomic numbers from 1 to 20 that you have to know. In addition to that, there are so many other elements. About 115 elements are here. As you can see, the elements in the periodic table are arranged according to ascending order of atomic number, and you can see a pattern here. All this part of the periodic table is colored in blue because these elements show metallic character. We call them metals, whereas the light brown color region are non-metals, similarities. The dark brown region is the noble gases. And you can see there is a zigzag step-like pattern there. These are shown in green color and they are known as metalloids. We will be discussing these types and their properties later in the lesson. Now we will look at the nature of the periodic table. And these are the elements that have been identified so far. And here we have the numbers. This side you can see is numbered as 1, 2, 3, 4, 5, 6, 7, 8 or 0. We will call them the groups. They are known as the groups. You might be wondering why the 2 groups are here and the rest of the 6 groups are on this side and there is a space here. Yes, the reason is if you look at the increasing order of atomic number, 3 and 4 are here, 5 is here. In order to fill the space, if we had the 5 there, the properties will be different. We need to have only the metals here. Now, boron is a metalloid. So, if we put boron here, the properties will not show a proper pattern. That is the reason it has been pushed to this side. And again, here there are a lot of elements which we will not be looking at, but they are also metals. So, now you have a good understanding, a basic understanding about the periodic table. And out of this periodic table, this is the full periodic table, we will only look at the first 20 elements. So, then we will be using a simple form of periodic table. I will explain the rest of the information using that simple format. As you can see here, this is a part of the modern periodic table, and here we only have this part with the first 20 elements. And the space between this beryllium and boron and all the elements there have been taken out. Only these 20 elements are shown. In this, the vertical groups are known as groups. The vertical columns are known as groups. Vertical columns. The vertical columns, which are called the groups, as you can see, are given the Roman numbers. That also the capital numbers has to be used. So here you have to remember, students, you have to use the Roman numbers. Then we have the horizontal rows. The horizontal rows, these are the horizontal rows. These are known as the periods. They are called the periods. And periods are numbered as 1, 2, 3, 4. Because 4 periods are enough to accommodate the first 20 elements. And you can see the periods are numbered with the normal Arabic numbers. So groups, you have to use the Roman numbers. For periods, you can use the normal, or you have to use the normal numbers. This is the basic format of a periodic table. And as we discussed before, this obeys the periodic law. So all the elements in group 1, but here the exception will be hydrogen, lithium, sodium, potassium will have similar properties. Beryllium, magnesium, calcium will have similar properties. Fluorine and chlorine will show similar properties, and group 8 or group 0, helium, neon, argon will have similar properties. So that is what we mean by elements with similar properties will recur at regular intervals, the periodic law. Now we will see how we can arrange these elements into different groups and periods. First, we will see how we can divide elements into periods. If we take an example, you look at the simple part of the periodic table. If we take hydrogen, hydrogen is an element that has only one electron. So the electronic configuration is 1. Helium is another element that has 2 electrons. The electronic configuration is 2. Then the third element is lithium with 3 electrons. So the electronic configuration is 2 and 1. Here you can see the first 2 elements, hydrogen and helium, have electrons only in their first energy level. The first energy level can accommodate a maximum of 2 electrons, and hydrogen has 1, helium has 2. These 2 elements belong to the first period of the periodic table. So that means if an element has only the first energy level, carries electrons, then those elements go to period 1. Then we look at the second example, lithium. Lithium 2,1. Similarly, if we take another example, nitrogen. Nitrogen has 7 electrons. So, the electronic configuration is 2, 5. If we take neon. Neon has 10. So, it's 2, 8. So, all the elements starting from lithium up to neon, atomic number 3 to 10, they will have electrons in the first and the second energy levels. And these elements belong to the second period of the periodic table. So, if we look at the elements, only the first and second energy levels carry electrons, then they will go to the second period or period 2. Likewise, we take elements from here, atomic numbers starting from 11 to 18. I will take an example, magnesium. If we write the electronic configuration, it will be 282 because the atomic number is 12. And if we take, let's say, sulfur, atomic number you can see 16. In this periodic table, you would have noticed that atomic numbers are not written according to the standard format of the symbol because this is not the standard format. It's the element that is denoted and the top right hand corner shows the atomic number. That is the way to use it in the periodic table. So here you can see sulfur atomic number is 16. So the electronic configuration will be 286. In these two elements and all the other elements starting from sodium up to argon, atomic numbers 11 to 18, they have electrons in the first, second and third energy levels. Only the first, second and third energy levels carry electrons. So that means they all belong to period 3. They are all in period 3. Now we will look at the last two elements, potassium and calcium. So as you can see, the atomic number of potassium is 19. So if it is 19, when we write the electronic configuration, it's going to be 2, 8, 10. Do we write 9? No. We have to write 8 here and the last electron will go to the fourth energy level because we can't have more than 8 electrons in the outermost energy level that contains electrons. Similarly, for calcium, atomic number is 20. So, the electronic configuration will be 2, 8, 8 and 2. You can see, students, in these two elements, electrons are present in the first 4 energy levels. So, therefore, they come in the fourth period of the periodic table. As you can see, only the first, second, third and fourth energy levels carry electrons. Then they go to period 4. Now you might be wondering why we say only the first, second, third and fourth. For us, we are only looking at the first 20 elements. So we are using only the first 4 energy levels. But there are more than 4 energy levels. That is why we have to say only the first, second, third and fourth energy levels carry electrons. And then the elements come to period 4. So now you have understood how the elements are arranged into different periods depending on the number of energy levels that contain electrons. We will see some more details. Here you can see these are the elements in ascending order of atomic number and how they have been classified into different periods. So the first two elements, hydrogen and helium, because they have electrons only in the first shell, they go to period 1. Elements from lithium to neon, atomic numbers from 3 to 10. They have electrons in the first and the second energy levels. That is the K and the L shells. Then they all go into the second period of the periodic table, period 2. We look at the other elements, sodium to argon. Atomic number of sodium is 11, atomic number of argon is 18. So elements with atomic number 11 to 18 have electrons in their first 3 energy levels, the K, L and the M shells. So therefore, all these elements are present in period 3 of the periodic table. And the last two elements that we should know, potassium and calcium. They have electrons in the first 4 energy levels, K, L, M and N. Then they go to period 4. So this is the relationship between the period number and the number of energy levels containing electrons. If we put that as a note, we can say period to which an element belongs to is equal to the number of shells that contain electrons. That is the relationship between the period number and the number of shells. And that is how we arrange elements into periods. When I started explaining periodic table, I told you that the periodic table elements have been arranged based on their atomic number and the electronic configuration. So, atomic number, elements are in ascending order of atomic number, and this is the relationship between electronic configuration and the periodic table. Next, we will see how elements are grouped into groups. Dividing elements into groups. The properties of an element depends on the number of electrons present in its outermost energy level. You saw that these elements, for example, lithium to neon, they are there in the second period of the periodic table. That means they have electrons in the first and the second energy levels. But they are different elements, atoms of different elements. The difference is they have different number of electrons in the second energy level. Lithium 1, beryllium 2, likewise when we go to neon, it had 8 electrons in its second energy level. Same for the elements of the third period. They had 3 energy levels that have electrons, but the number of electrons in the third energy level varied from 1 to 8. So because of that, the number of electrons present in the outermost energy level is given a special name, valence electrons. So here, if we take elements along a period, they have different number of electrons in their last energy level. Therefore, they are grouped into various groups, or they are divided into groups starting from group 1 to group 8. And group 8, as you know, is also known as group 0. We will look at some examples. We will take lithium first. If we take lithium, lithium has atomic number 3. So the electronic configuration will be 2 and 1. Here, the last energy level, that is because it contains the valence electrons, we also call it the valence shell. So as a note, I will write it here. The last, no, we can better say outermost energy level, most shell that contains valence electrons is known as valence shell. So here you can see valence shell has only one electron. Then that element will go to group 1 in the periodic table. If you look at all the other elements in that group, sodium, atomic number 11, so electronic configuration is 281. Again you can see it has only one electron. Potassium, atomic number 19, electronic configuration 2881, again 1 electron. So all these 3 elements go to group 1. Group 1. We look at some other elements, carbon and silicon. Carbon has atomic number 6, so the electronic configuration is 2, 4. 4 electrons in the valence shell or the outermost shell. So it belongs to group 4. Similarly, we take silicon. Silicon has atomic number 14, 2, 8, 4. That also has 4 electrons in the valence shell. So this goes to group 4. And here you can see we have to use Roman numbers to denote groups. Same way, we take the elements helium, neon and argon. Helium has only 2 electrons. Neon, the atomic number is 10. So the electronic configuration is 2, 8. And argon, atomic number is 18. So it's 2, 8, 8. Here you can see these two have 8 electrons. So therefore they go to group 8. But helium Helium has only 2 electrons. It also goes to or belongs to group 8. The reason is having a full energy level. That is an energy level with maximum number of electrons possible is a stable electronic configuration. So therefore, any element here with a stable electronic configuration also goes to group 8. Therefore, these three, helium, neon and argon, all of them belong to group 8 or group 0. Group 8, also known as group 0. When there is a stable electronic configuration. So, this is the relationship between electronic configuration and the group to which an element belongs to. Again, to summarize, the periodic table is based on atomic number and electronic configuration. Elements are arranged in ascending order, that is the increasing order of atomic number, and the number of shells that contain electrons in a particular element will be equal to the period number where the element is. And also the number of electrons in the outermost energy level will be equal to the group number of that element. With that in mind, we will see how elements are grouped or arranged into periods and groups in a periodic table. Number of electrons in the outer energy level is given to you. So, based on that, we arrange these elements into different groups. Here you can see if the element has only one electron. If the element has only one electron, it belongs to group 1. Element has 2 electrons, it's group 2. 3 electrons, group 3. 4 electrons in the outermost energy level, group 4. 5 electrons in the valence shell, group 5. Outermost energy level, valence shell, all refer to the same thing. And also valence electrons are the number of electrons in the outermost energy level. So, I am just using the different terms so that you can become familiar with all the different terms. Then valence electron 6, it belongs to groups 6. 7 electrons in the valence shell, group 7. And 8 electrons in the outermost energy level, or as I said before, stable electronic configuration. Then the element belongs to group 8 or group 0. Here is a summary of the elements, atomic number, electronic configuration and the group to which the elements belong. You can see hydrogen, atomic number 1, electronic configuration 1, so it belongs to group 1. Helium, atomic number 2, electronic configuration 2, it belongs to group 8 or 0. It's the same group. Lithium, atomic number 3, 2, 1 is the electronic configuration. Again, because it has 1 electron in the valence shell, group 1. Beryllium, atomic number 4, 2, 2 electrons, so it's group 2. Boron, atomic number 5, electronic configuration 2, 3, 3 valence electrons, so group 3. Then carbon, atomic number 6, electronic configuration 2, 4 and the valence electrons are 4. Therefore, it belongs to group 4. Nitrogen 7, 2, 5 is the electronic configuration. So, it goes to group 5. Oxygen 8 protons, therefore atomic number is 8. Electrons are also 8. 2, 6 is the electronic configuration, group 6. Fluorine, atomic number 9. 2, 7 is the electronic configuration, group 7. And finally, neon, atomic number 10. 2, 8 is the electronic configuration, and here you can see it goes to again group 8 or group 0. To the other elements now. Sodium to argon, atomic numbers are increase starting from 11, 12, 13, 14, 15, 16, 17, 18. So accordingly, you know when you write the electronic configuration 2, 8. The first two energy levels are completely filled, but the third energy level is getting filled. Sodium has 1, magnesium 2, aluminium 3, silicon 4, phosphorus 5, sulfur 6, chlorine 7 and argon 8. So that means their group varies from 1 to 8. Sodium group 1, magnesium group 2, aluminium group 3, silicon group 4, phosphorus group 5, sulfur group 6, chlorine group 7 and argon group 8. That is the relationship again between electronic configuration and the periodic table, or the position of the element in the periodic table. There are two more elements that you need to remember, that is potassium and calcium. If we write potassium here, atomic number 19, electronic configuration 2881. So it belongs to group 1. And the last element that you should remember, calcium, atomic number 20, electronic configuration 2882, and that will belong to group 2. So now we have arranged or divided the first 20 elements into periods and groups. We will see how we can identify the position of an element in a periodic table. How to find the position of an element in the periodic table. So, for example, if they give you the atomic number of an element. So, the atomic number of magnesium is 12. That means there are 12 protons, which is equal to the number of electrons. So, there are 12 electrons in an atom of magnesium. We will now distribute these electrons into their energy levels. Out of the 12, the first 2 electrons will go to the first energy level, that is the K shell. Then we have another 10. Out of those 10, 8 more electrons can go into the second energy level, that is the L shell. 2 and 8 electrons, 10 electrons have been assigned. There are 2 more electrons. They will again go into the last energy level or the outermost energy level, or what we call as valence shell. And these 2 electrons are the valence electrons. So, if we write the electronic configuration using this, magnesium electronic configuration is 2, then we have 8 in the second shell, again 2 in the third shell. So how do we identify the position? The number of shells containing electrons will be equal to the period. So number of shells that contain electrons is equal to period. So here it is period 3. How do we identify the group number? The number of valence electrons. Magnesium has 2 valence electrons, so it has to belong to group 2. Number of valence electrons equals group number. So here there are 2. That means magnesium belongs to group 2. So as you can see, magnesium is present in period 3 and group 2. So these are the position of the element magnesium. We will look at another example. Atomic number of potassium is 19. So then we need to allocate the electrons first. In the first energy level, there can be 2 electrons. Second energy level can have 8 electrons. So we have allocated 10, another 8 to the third energy level. So we have 2, 8, 8, that is 18. But there are 19 electrons. So there will be 1 electron in the outermost energy level or the valence shell. From this, we can write the electronic configuration 2, 8, 8, 1. How do we identify the position? Yes, the number of shells that have electrons in them, there are 4 shells. So that means potassium belongs to period 4. What is the group? Yes, the number of valence electrons is equal to the group number. So here there is only 1 valence electron. That means potassium belongs to group 1. Now you have identified the position of potassium in the periodic table. We will look at another example. Atomic number of oxygen is 8. That means oxygen has 8 electrons. So now we will do it in a different order. We will first write the electronic configuration, then fill up the electrons here. Because directly from the atomic number, you should know to write the electronic configuration. So when there are 8 electrons, electronic configuration will be 2 and 6. 2, 6 is the electronic configuration. That means there are 2 electrons in the first energy level and there are only 6 electrons in the second energy level. If you count 1, 2, 3, 4, 5, 6 electrons in the second energy level. So only the K and L shells are filled up here we know the electronic configuration. So you know to identify the position, the period number and the group number. Here, oxygen belongs to what period? There are two shells with electrons, so it has to be period 2. And what is the group number? You know to calculate it, you know to identify it. Yes, since there are 6 valence electrons, the group number will be 6. So students, now you have a very good understanding about identifying the position of elements in the periodic table. With that in mind, we will summarize the period number and the group number of elements in a periodic table. Groups and periods of first 20 elements. So here you can see the atomic number is given. You know the elements, and by now you would have memorized the correct order of the first 20 elements. And you know to write the electronic configuration. Using these two, you will be able to identify or find the period of the element and the group of the element. The first two elements, hydrogen and helium, they only have electrons in the first shell, so they both belong to period 1. But the groups are different. Hydrogen belongs to group 1 and helium belongs to group 8 or group 0. Why? Although it has 2 electrons, it doesn't go to group 2, but it goes to group 8 because the maximum number of possible electrons are there, and also it is a stable electronic configuration. So it's group 8 or group 0. Then the third element, lithium, 2, 1. So it belongs to period 2 and group 1 again. Beryllium, group period 2, group 2. Boron, period 2, group 3. Carbon, period 2, group 4. You can see all these elements have electrons in the first 2 energy levels. So period 2, but the group changes based on the valence electrons. Then we have nitrogen, period 2, group 5. Oxygen, period 2, group 6. Fluorine, period 2, group 7. And finally, neon, period 2 and group 8 or group 0, the same group. The next set of elements, sodium, atomic number 11, 281. So this goes to period 3 and group 1. Magnesium, period 3, group 2. Aluminium, period 3, group 3. Silicon, period 3, group 4. Then we have phosphorus. You can see the electronic configuration 2, 8, 5. So 3 shells with electrons, period 3, and the valence electrons are 5. So group 5. Sulfur, again 3 shells with electrons. So period 3 and 6 valence electrons, group 6. Chlorine, period 3 and group 7. Again argon, 288, complete energy level, stable electronic configuration, and also 8 electrons in the valence shell. So it belongs to period 3 and group 8 or 0. The last two elements, potassium and calcium, they both have 4 energy levels containing electrons. So, they both belong to period 4. Potassium has only 1 electron in the valence shell, so group 1, and calcium has 2 electrons in the valence shell, so this goes to group 2. Now, we have divided the first 20 elements into their periods and the groups. So, with these students, you have a very good understanding about writing atomic numbers, mass numbers, standard symbol, dividing electrons into their shells, that is the electronic configuration, then arranging them into periodic tables and identifying the position of elements from a periodic table. If they ask you, identify the position of phosphorus in the periodic table. So, immediately you have to remember phosphorus has atomic number 15. Therefore, electronic configuration is this 285. 3 shells containing electrons. Therefore, it belongs to period 3. And in the valence shell, there are 5 electrons. So, it belongs to group 5. The same way, if they tell you, I'll go back to the slide, there is an element that is present in period 2, group 4. Identify the element. Then you see, okay, period 2, group 4. Here you can see all these are period 2 elements and here we have group 4. So, group 4 and period 2, the electronic configuration has to be 2, 4. Then the element will be carbon and the atomic number 6. You can either start from atomic number and find the position, or from the position you can come back to its atomic number. That is one of the advantages of arranging elements into the periodic table.